All right, so this next section is on the distribution of the sample proportion. So it's very, very similar to what we were doing. The main difference is instead of working with mean values, like the mu and the x bar values, we're working with proportions. So it may be a percentage or a fraction. Okay, and everything that we were doing with the tables, finding probabilities, that all extends to proportions or percentages. All right, so if you feel like you're a little bit behind on what we did in the last section, just know that what we do or what we did is going to be similar to this. So hopefully this can kind of reinforce some of that. But, you know, we have like a population value and we have a sample value, right? Just like we have our population mean is mu and our sample mean is x bar. Well, same thing. We have a population mean, a population proportion that will be like P. That's the population proportion. And we have P hat. You know, it looks like a P that's wearing a little hat right here. That is the sample proportion. And since P hat does come from a sample, if you ever have to figure out P hat and it's not given, a lot of times it's just given to you as a percentage. But if it isn't given, then P hat is just going to be part over total of your sample. So like the number of observations that you want in your sample over the total number in your sample. So then you could change it to a decimal or a percentage or whatever you wanted to do with it. So how do we say this thing? P hat. All right, so every time I say P hat, you know what I'm talking about. Now, one thing that we went over in the last section also was the central limit theorem. And what the central limit theorem does is it allows us to figure out probabilities about groups of data. So, for example, when we started out talking about normal distributions and their applications, we were doing things like what's the probability if I randomly selected one person that their IQ is over 80. But when we got to the central limit theorem, that allows us to take a group of people and try to figure out a probability about a sample group. So for example, let's say that I took every statistics student that I'd ever taught, and that was my population. And then I took a sample of all of you in here. Then I could say something like, what is the probability that the test average on test 2 is greater than 75% with a sample size of n equals 28, or how many people we have in here. So that's a central limit theorem if you take a group of people and you're trying to do find a probability for them or about them. All right. And so remember that changes your z-score formula just a little bit. So in the last section, or a few sections ago, we wrote down z equals x minus mu over sigma. And that's the normal z-score formula. But when we introduced the central limit theorem, where we're looking at groups of people, this was a sigma sub x bar in the denominator. So with the central limit theorem, remember sigma sub x bar was equal to sigma divided by the square root of n, because we were looking at finding probabilities for a group of people. And so that n is that sample that we take out of the population. Well, I bring that up because if we're going to start doing the same thing that we were doing, but we're going to be using proportions, then a couple of things have to change. Okay? We're not going to have just an x value anymore, because we don't have a sample mean or an x bar. You know, sometimes we're using x for x bar. So instead, we're going to have a p hat. So that's what comes from the sample. So our new z-score is going to be p hat minus, and then before it was the population mean. Well, now it's the population proportion. So it's going to be p hat minus p over, okay, now again, if we use the central limit theorem with this, then instead of having a sigma, we're going to have a sigma sub p hat. Okay, because we have to take into account, if we're talking about a sample or a group of people, and we're trying to figure out a probability about a proportion of a group of people or a group of subjects, then that has to factor into my sigma sub p hat. All right, and that formula is, for sigma sub p hat, is the square root of p times 1 minus p divided by n, where p is the population proportion and n is the sample size. Now, you may be wondering why we don't use p hat there instead of p. And that's because it is kind of an approximation, but we know for sure that p is a true value of the population. We don't know that p hat is a true value. It's something that we're testing. We're like doing a little test on it. Okay, so we use our p value, not our p hat value, when finding this sigma sub p hat. All right, so to complete the formula, it's divided by sigma sub p hat. And if you were just to write sigma sub p instead of sigma sub p hat, I wouldn't really count off, because we're using p to find the values. So whatever makes it easier for you to remember. All right, so let's look at a sample problem on how we could use this to figure out some type of probability. And this comes from your PowerPoint. So we are in 9.4 on the PowerPoint. And it says, suppose a sample of 400 persons is used to perform a taste test. If the true fraction in the population that prefer Pepsi is really 0.5, what is the probability that less than 0.44 of the persons in the sample will prefer Pepsi? All right. Excuse me. So I'm just interested. I try not to drink many carbonated beverages, and when I do, they're usually diet Cokes or diet or Coke Zero or whatever. But if I was forced to choose between drinking a Coke and a Pepsi, my personal preference is Coke. If I have to drink one. How many people in here would rather drink a Pepsi than a Coke? Just be honest. Nobody? And I've kind of I don't know if that's a thing in the South or what. I don't enjoy Pepsi really, or Diet Pepsi for that matter, as much as I do a Diet Coke. So I don't know. This problem to me kind of starts off weird if the true value is really 0.5. I don't know that I believe that. Okay, anyway, so in this problem, we know that P, the population proportion, is 0.5. All right. Now, we also know that N is equal to 400. That's the sample size. And we're trying to figure out that the probability that P hat is less than 0.44. Okay, what am I missing that I need to find a z-score? I'm missing my standard deviation, or my sigma sub p hat. And we just wrote down a formula for that. All right, so let's calculate that. And remember, we use the population values to find this. So it's 0.5 because it tells us that if 50% or 0.5 prefer Pepsi, so it's 0.5 times 1 minus 0.5. What's 1 minus 0.5? 0.5, right? Over 400. Now, the most common mistake here that students make is they'll work out the inside, but then they forget to take the square root at the end. And I say students because I'm a student as well, and I've made that same mistake. So make sure after you do all this stuff here that you take the square root. If not, then we have the variance, right? So we got to take the square root to get the standard deviation. All right. So you can see that's a super small number, but what do I have to remember to do? Take the square root. It's still pretty small, but now it's a little larger than it was. So 0.025. All right. So remember, our formula is going to be p hat minus p over sigma sub p hat. All right. So z equals, that's going to be 0.44 minus 0.5 over 0.025. All right, so remember, for z-scores, we always round to 2 places. So here's another tip. When you're plugging your values in, especially your sigma sub p hat into your formula, if when you calculate that, that goes out and it's not a terminating decimal, meaning it goes out and your calculator shows you like 8 places, at least take that out to 5 or 6 places. The reason for that is, if I plug a rounded value in there, and then I divide that, and then I round the next value, it creates a large margin of error. So even 5 or 6 places is rounded. it's a rounded value. But since you will always round your z-scores to 2 places, then taking that out to 5 or 6 places is okay. All right. I've learned from experience. I've gotten problems wrong and sat there and wondered why, and it was because I tried to round too early. Try not to round very much, or at least to 1, 2, 3 places until the very end, if you can. So when you do that in your calculator, it just so happened we got negative 2.4. Well, the way our z-score charts work, I need to put a 0 on this, right? Because we have to have 2 decimal places. Now, this was a less than problem. So less than problems, we want the area to the left. And that's the way that our z-score charts work. So to me, they're the easier problems, because all we do now is pull up our z-score chart. So this is the one that comes with your formula sheet. All right. And it even has this little graphic up here to remind you, hey, look, this chart is going to give you the area cumulative from the far left all the way till you get to the z-score. And that area corresponds to a probability. That's why we use these. All right, so we want to go to negative 2.40. Now notice up here too, also the hundredths place starts with 9 on the negative z-scores. It starts with 0 on the positive, but it starts with 9 on the negative z-scores. So if we want to go to the 0 at the very end, we got to use the last column. So it's going to be negative 2.40. So 0.0082. And since it was a less than problem, that's my actual answer. That was my area. So my probability is 0.0082. Just like that. All right. Any questions on that one? Let me pull up one from the homework and we can work it out. If I could just click on the right button, I will bring it up, I promise. Let's see. All right, here we go. I want to do a greater than problem, so yeah, here's one here. All right, this says, suppose 56% of the students at a university are baseball players. That would be a lot of baseball players. Maybe people that have played baseball in their lifetime, but definitely not that many at a university. You'd have, I guess you'd have a team and a JV team and a A, B, C, D team. I don't know. Anyway, if a sample of 840 students is selected, what is the probability that the sample proportion of baseball players will be greater than 51%? Round your answer to 4 decimal places. Most of these on the homework say 4 decimal places. And that's because when you look in the tables, they give you 4 decimal places. So it says, suppose 56% of the students are baseball players. So that's something that we're having to just kind of take and say this is a true statement. That is our proportion P. So would I want to write 56%, or how would I want to write that? 0.56, right, as a decimal. It's easier to work with those decimals. All right. We have a sample size of 840. And we want to know the probability that the sample proportion of baseball players will be greater than 51%. So P hat is 0.51, and we're looking for the probability that P hat is greater than 0.51. All right, so to figure out our z-score, to standardize these values like we did with means, the first thing we have to do is figure out what's not given and what we have, which we've written everything down we have. So I didn't see a standard deviation, so I need to figure out my sigma sub p hat. All right, that's going to be the square root of, let's say, p, so that's 0.56 times 1 minus p. So what's 1 minus p? Point what? 44? If you say 1 minus 0.56, you should get 0.44. Alright, we have to use the 0.56, not the 0.51. Remember, we're always going to use the population values when we're finding the sigma sub p hat. Alright, divided by n. And n is 840. Alright, I'll be surprised if this is a real pretty decimal, terminating decimal. 0.56 times 0.44 equals, divided by 840 equals, and then take the square root of that. Alright, so what I'm going to do to cause less margin of error is I'm going to take this out about 6 places. So if I take this out 6 places, I have a 9 after the 6th place, so I'm going to turn that 6 into a 7. So 0.012127. Alright, so whenever I use my z-score formula, I'm going to plug that in. So now let's use our z-score formula and find our z-score. Z equals, remember, it's always going to be the sample value, so p hat, minus the population value, divided by that standard deviation, or sigma sub p hat. Alright, so that's going to be 0.51 minus 0.56 over 0.017127. All right. I got to round this to 2 places. Negative 2.92. All right. This is a greater than problem. And with greater than problems, that means the area to the right. So just to show you a picture of what we're doing. Remember, the z-score in the middle is always 0. This would mean a z-score of negative 2.98 means I need to go 2.9, I said 2.98, 2.92. Negative 2.92 means I need to go to the left almost 3 standard deviations. So I'm just going to guess that about right here is probably a z-score of negative 2.92. Now this is a greater than problem. Greater than means area to the right. So if this entire thing, this entire space under the curve is equal to 1, it looks like I've almost shaded in the whole thing. So whenever I find my final answer, it better be high 90 percentages, or maybe even 99 point something. Okay? Now, when I look in my table though, remember it's going to give me this right here, right? It's going to give me just this little piece right here because the table gives me the area from the far left all the way up to the z-score that we're looking at. Okay? So let's do that. Let's look up and see what the area is for a z-score of negative 2.92. So look at your z-score chart. Negative 2.9, and then go over to the 2. You see that right there? 0.0018. So that is a super, super small number. So to find my answer though, I want the area on the right. So I say 1 minus 0.0018. And what's that equal to? 0.9982. So that's what I need to put in for my answer. So that actually means there's a 99.82% chance that if we take a sample of 840 students at that university, that more than 51% of them play baseball. All right. Let's do one more because this one is a little tougher. Because this is one of those, like in the last section, where you're looking for a probability that differs or, is less, differs by a certain percentage than the population percentage or proportion. The one where we have to add and subtract to find our on this it'd be our p-values. Okay. So read this problem. What is myopia? Do we know? Wonder if it's what I think it is. No, it's not. I get scared when I look at things on the internet sometimes. I was thinking about somnia. Myopia is nearsightedness. So people that can see close but can't see far. And that is what I had until I had eye surgery. The best money I've ever saved. All right. So we're given the population proportion P is equal to 0.48. So that's like, it's talking about everybody alive, pretty much, on the whole planet. This is, we're assuming that or supposing that. So if we take a sample of 484, So we go pick out 484 people randomly. What is the probability that the proportion of persons with myopia will differ from the population proportion by less than 3%? So if you're going to differ by less than 3%, that's going to include 3% more and 3% less. So we're going to have two values that we have for our p-hat. You can name them differently, like a sub 1 and a sub 2 if you need to do that to keep them straight. But if I add 3 percentage points to 48%, that would be 51%, right? So that would be 0.51. And then if I subtract 3 percentage points from that, that would be what? 45. The good news is, even though we do have to find two z-scores, we only have to find one standard deviation because we use the same standard deviation with both of these. So we need to find our sigma sub p-hat. Our sigma sub p-hat is going to be the square root of, and remember we always use the population proportion here. So it's 0.48 times 1 minus 0.48 is 0.52 divided by 484. And I'm going to do that in a calculator and take it out to a bunch of places. Don't forget to take the square root after you get your values underneath. Alright, so 0.0227, and then I'm going to say 0.9. So 0.022709. 0.02709. Alright. So since this is a problem where you wanted to differ less than, this is going to be between the two z values we get. If it would have said more than 3%, we would still find the same p-hat values. It's just we would have to take the error on the outsides of each of the two. And when I say inside and outside, I'll draw it up here and show you. But we have to have the z-scores before I can draw it. Okay? So let's find our z-scores. So z equals, it's always the sample first. So 0.51, the sample value, minus 0.48 divided by 0.022709. Alright, so I always round my z-scores to two places. So this is going to be a positive 1.32. Now I bet you there's somebody in here that can tell me the other one without even working it out. Negative 1.32. Alright, I'm going to show you how. But if I put in the other value, 0.5 or 0.45 minus 0.48 over 0.022709 equals, so here's why. When I type in the numerator, if I type in 0.45 minus 0.48, I get the same number that I got before, except it's negative. So when I divide by the same denominator, that just means I'm going to get the same answer, except it's going to be negative. That's negative 1.32. The reason that is because we went 3 percentage points above and 3 percentage points below. So when we standardize that value, we will have the same z value, except one will be positive and one will be negative. That will always happen if you go the same amount above and below the population mean. All right, so really you only have to work one of those out if you're wanting to save time. So what would the picture look like? Well, we have our standard normal curve here. Right here in the middle, we'll remember z equals what? 0. Z-scores to the right of the middle are positive. Z-scores to the left of the middle are negative. All right? So if I wanted to go 1.32 out, I'm just going to guess. Let's say that this is 1.32 standard deviations to the right. And let's say this is negative 1.32 standard deviations to the left. All right, what we're looking for, since it will differ by less than, we want to know the percentage between the two, or the area between the two. That will give us our answer. If we figure out the area, we figure out the probability. So how do we do that? Well, remember I told you the easiest way to do that is to take the z-score to the far right, find that area, and then take the z-score to the far left and find that area, and say the bigger area minus the smaller area, because of the way our tables work, will always give you the area between the two. Now, if you start using table C instead of table A and B, that's not going to be true. So make sure you're using table A and B. Alright, so since I'm already here, it doesn't matter which one you find first, really, because you just say the bigger area minus the smaller area. You can't get a negative area. If you do, you messed up. Remember, probability can't be negative either. Alright, so negative 1.32. So remember the column the 2's are in. They're in this column right here. Negative 1.32 is right there. So I got 0.0934. So this area over here was 0.0934. And now positive 1.32. Positive 1.32. 0.9066. So we say the bigger number minus the smaller number. All right, so the answer that I got was 0.8132. So that means, so that's the answer you'd want to enter in. That means that 81.32%, that's the chance that if I was to randomly select 484 people, that they would, I guess we could say, there's between a 51% and a 45% chance that they would have myopia. 81% of those, the people selected. So if this would have been by more than, then we would have wanted the area on the outsides. So we could do the exact same thing that we did here and say 1 minus that, and that'll give us the area on the outsides.